Yesterday was talking about inverses and looking at how inverses and graphs of those inverses all go together and identifying if it's a one-to-one function and that kind of thing. Today we're going to talk about an entirely different function that we haven't really seen yet. It's going to kind of look similar to some of the graphs that we saw in chapter 4, but it's just a little bit different. Okay, so exponential functions, and you've seen these back from Algebra 2. So when you say, well, maybe you've seen these before, you have seen these before. Today we're going to talk about what an exponential function is. We're going to talk about shifts or transformations of an exponential function, and then we're going to look at some kind of story problems or money problems that are related with these exponential functions. So to start off with, the basic general equation for an exponential function is f of x equals a raised to the x. And we call it an exponential function because our variable is in the exponent. Okay? Usually, like if I say 2x plus 3 or 2x squared or something like that, then my variable is never in the exponent. So this is the one function where the variable is in the exponent, and that's how we can identify an exponential function. And that's why it's going to be a little bit different than some that we've seen. One of the things that we'll have to remember is that a cannot be 1, because if the base of my exponent is 1, 1 to anything is always going to give me back 1. Okay, so we don't want to see a base of 1. My base could be two different things. My base, if a is bigger than 1, if a is greater than 1, then we call it a growth function. And so that would be something like f of x equals 2 to the x. Any number bigger than 1. 2, 3, 4, 5, whatever. Variable is still x. If a is less than 1, but not only less than 1, but somewhere between 0 and 1. We don't want it to be negative, because negative will have a different change to the graph. So now we're looking at numbers like a half, a third, a fourth, some kind of fraction, something between 0 and 1. Then we call this a decay function. And so in this case, it would be f of x equals 1/2 to the x, as an example. So those are your two basic exponential functions, a growth function, and I'm going to show you what it looks like here in just a second, how we can find out what some values are really quickly, and then what a decay function looks like, and then we're going to talk about some transformations of the two of those. Okay, I'm going to do these side by side. I'm going to graph the two that we just did. We're going to do a growth function, and we're going to do a decay function. And I'm going to use the two functions that I just gave you. F of x equals 2 to the x. F of x equals 1/2 to the x. Now, can I graph this in my calculator? Absolutely. Okay, your calculator will graph this, and you can get points from your calculator, just like we've talked about with any other function and graph that we've done throughout the entire semester. Okay, it can be a pretty big help. But I want to talk about some of the special things that happen on exponential functions that happen for all of these, and things that we have to identify or recognize based on the information that we know. Okay, so to start off with, coming up with a few points. Okay, and like I said, if you want to come up with these from your calculator, that's okay, but I think it's also important to understand where do these numbers come from and why do we get the numbers that we get. 0 is always a good go-to, right? We always use 0. It's kind of like our starting point. If I plug in 0, 2 raised to the 0 would be 1. Anything raised to the 0 power is always 1. We haven't really talked a lot about all of our exponent rules throughout college algebra, but that's something that goes back to some of the things that we've talked about in prior years where we got to remember some of those exponent rules. An exponent of 0 always gives me 1. If I take 2 to the first power, it gives me 2. If I do 2 to the negative 1 power, here's another exponent rule that we haven't really seen much throughout college algebra, but we have seen it before. When I have a negative exponent, what does that do to my number? Anybody remember? Negative exponents. Flips it. Yeah, good. And so it would make it 1 over 2 to the first. It flips it, and when I move it to the denominator, it makes it a positive exponent. And so 2 to the first is really 2, so this would become 1/2. So if I graph this, zero, 1 is going to be right there. 1, 2, and then negative 1, 1/2. Okay, and we could put this into our calculator and see what the graph is going to look like. But there's a couple of things here I want to point out. Okay, first of all, on a growth function, that graph is going to grow as it moves to the right. Okay, and that's why we call it a growth function. It's going to start as I move from left to right. That graph is growing and it's getting faster really quickly, right? And here's why I told you it kind of looks like the ones that we did in chapter 4, right? But there is no vertical asymptote here. There is no asymptote over here on the right where it's approaching. It's going to keep moving to the right, and it doesn't have an asymptote that it's approaching vertically, but it does have one horizontally, okay? And in this case, as long as we don't move that graph up or down, then my horizontal asymptote is y equals 0, which is that x-axis right here. The equation is y equals 0, but the x-axis is how we usually think of it. Okay? And so it's getting really, really close to that x-axis, but it will not cross it or touch it. Okay? And so it is an asymptote. And so that's the one thing where it is kind of similar to some that we saw in the previous chapter. Okay, so those are some common things. One of the things that you'll notice, as long as there's no movement or shifting, all of these functions are going to cross at 0, 1. Because when I plug 0 into my exponent, it's always going to give me a value of 1. I will talk about like some shifting here in just a second and how that takes place and how that changes things. Okay, now if I put 1/2 into, for my a value, and just kind of see the differences between these two to kind of compare them. And you can plug any numbers in that you want to, right? It doesn't really matter the numbers you plug in. You can go to your calculator, you can go to your table of values, you can get some points right from that. But once again, I think it still is important to understand where are these numbers coming from. They don't just come out of thin air. There's a reason why we get the y values that we get, and that's because of the exponent that we have. So once again, when I plug 0 in as the exponent, anything raised to the 0 power, no matter what that base is always going to be 1, okay, every time. So 0, 1. And that's the one common piece that these graphs will have. Whether it's growth or decay, it's going to cross the y-axis at 0, 1 every time, unless there's some kind of movement. And I'll show you what I mean by that here in just a second. Okay, then if I plug in 1, 1/2 raised to the first power, when I plug in 1 as an exponent, it just gives me whatever the base is. So 1 would be 1/2. And when I plug in -1, if I raised 1/2 to the negative 1 power, then what that's going to do is it's going to flip my fraction, kind of like we talked about over here, okay? I just want you to understand where this is coming from and why we get the numbers that we get once again. 1/2 raised to the negative 1 is going to take that fraction and flip it, and it's going to make it 2/1 to the first power, which is really just 2, okay? So it's going to kind of have the inverse relationship a little bit of what we saw on the first graph. If I go over 1 and up 1/2, if I go left 1 and up 2, still a curve, right? But this time the graph starts up, and now as it's coming down, it's getting smaller, okay? It's decaying. And so as it goes from left to right, the graph is decreasing. And I say decreasing because I kind of think of decrease and decay. They both start with D, to kind of help you to remember what the graph's going to do in that case. And that would be the case anytime we have an A value that's a fraction here, that's less than 1. Okay, so 0.5, 0.25, anything less than between 0 and 1. Once again, the one common piece here is that it's approaching that x-axis again. Okay, it's approaching y = 0. It doesn't have a vertical asymptote. These graphs will not have a vertical asymptote, but they will have a horizontal asymptote. Okay, and so that's a little bit why it's different than what we did in the last chapter. Okay, so that's the big difference between a growth versus a decay. They're both moving and it's a curve basically, but is it getting really large or is it getting really small? Okay, and you could use growth and decay can be used in a lot of different instances. I could talk about the population of a country that's growing really fast over time. It's probably not going to grow at the same increment over time, but it maybe grows really fast. Or in the same case, if a lot of people are leaving a country or a city or whatever, the population could decrease exponentially. And so we can see a lot of different examples of things that could be exponential growth, means it's getting bigger, or decay. If something is decaying, it's fading away and losing the amount that it began with. Okay. One of the things that we're going to see today, and I want to kind of tie this back to some things that we've done earlier. If I gave you y equals the absolute value of x, we knew that that was a v, right? It makes a v. If I change that equation to something like this, then we talked about the changes that are taking place with this graph, right? What would the +2 in this case do? Jackson? Left 2, okay? It's going to be opposite of whatever's attached to the x, so it's going to go left 2, and then what's the -3 going to do? Down 3, okay? So this is taking my original graph and moving it left 2 and down 3. And so what I, in doing here to show you this or kind of introduce it is, we're not going to see absolute value graphs today because that's not our topic today, but we have seen the changes, right? And we talked about no matter what type of graph we had, because earlier in the semester we did it with quadratics, we did it with absolute value, we did it with linear, we did it with all kinds of different functions, and we said here's our changes, but what symbol do I have? Do I have, sometimes this was an absolute value symbol, sometimes it was a square root symbol, sometimes it was exponents, but the changes all were the same. And so when I look at an exponential function, it's going to be the same thing, okay? It's going to have the same changes to it, but it's going to be with an exponential function. So once again, if I started with f of x equals 2 to the x, okay? And let's say this is my original function. And I want to look at a change of a graph Okay? And so some changes have taken place. Whatever is attached to the x is always going to move opposite of what we think. Okay? And it's always going to move left to right. So in this case here, the x minus 4, and here's what I'll tell you is if you're going to put this into the calculator, you might want to put that x minus 4 in parentheses. You can put these things in your calculator, but you got to be really careful about how you put it into the calculator. So this graph is going to move right 4, and it's going to move up 5. Same types of transformations that are taking place as with what we've talked about with other functions. Now, if I was going to graph this, okay, there's no doubt that you can use your calculator, okay? And I keep talking about that. Your calculator is a pretty cool tool here. What I want to show you here is I want to show you how that change takes place and some of the things that I would be looking for. Because you're going to have to graph something like this on a quiz or a test, okay? And here would be some things that I'm looking for. Can I use my calculator to get some points? No doubt about it. But what are some things that we're going to be watching for or looking for? So what I think would be the best is I'm going to graph the original function. Okay, and I'm just going to label that. That's the original, and that's kind of like the one we're going to compare it to, right? And so this new one is going to move right 4 and up 5. And we can kind of tell what that's going to do, okay? I could even take the points that I have here and move them all right 4 and up 5, okay? And that would be a good thing to go with. But just a second ago, we said that the horizontal asymptote was the x-axis, right? And so what's going to happen here, we only have the one asymptote, which is our x-axis right now. When I move this new graph up 5, that horizontal asymptote is also going to move up 5. So now when I go and draw this, okay, that is where my horizontal asymptote is now going to be. So now that's the line that it's going to approach. My graph cannot drop below this line. This is now my horizontal asymptote. Okay, that's a really important piece of the graph. Okay, so I'm going to put this into my calculator. I'm going to kind of show you what we get and just kind of show you what it looks like here. And you guys can do as I do mine. Some easy points to use to graph this. And you could do a few other points as well, but the biggest thing is I'm going to probably ask you what type of change has taken place, right 4 and up 5, and then I'm going to ask you to kind of graph it. Okay, in some cases it may not ask us to graph both, it may just ask us to graph the new one, but I always kind of like to graph both of them just to kind of compare the two and just kind of see what they look like. Okay, and it kind of backs up my movement as well. Like if I'm saying that it moves right 4 and up 5, then I kind of can tell by the look of that. Okay, one other one I want to do here. For a decay function, I want to do a transformation one with that. And once again, I'm going to go back to the one we started with earlier. This is my original. This is our comparison graph. And then if I write a new equation here, you're going to see some of these equations written kind of in a little bit different form. And what I want to show you here is this is not the way that we're used to kind of it being written, okay? I always like this part to be first, and then I like to have something after it. But they're not always going to write it like that. And so what I can do here is I can take this 5 and I could move it to the end. That way it's in more of the format that we're used to seeing it. And so I could rewrite this. The negative has still got to stay in front of the function, but I can move the 5 to the end. The 5 is positive, so it's going to stay positive. It's going to be plus 5. Okay, so two things here are happening, okay? First of all, we don't have anything connected to the x, right? So there's no movement left or right. What's the plus 5 at the end going to do? It's going to move it up 5, right? What's the negative in front of a function going to do to it? It's going to flip it over, okay? So this graph is going to move up 5, and it's going to flip upside down, okay? And those would be the two changes I'm going to identify. Up 5, and it's going to flip upside down. I like to kind of identify what those changes are and then make sure my graph kind of matches up with that, okay? You could do it the other way around too, but I think it's easier just to say, okay, does it really match up with what I think is happening? And if not, why is it not doing it that way? So if I were to graph these two on the same graph, and just like the others, you can put it into your calculator. We graphed the original function already. Okay. It's still going to move up 5, so we're still going to move the graph up 5. So y equals 5 is my horizontal asymptote again. That's the line it's going to approach. But instead of decaying and being on top of the asymptote, now it's going to flip upside down. Okay, and this is probably where using your calculator would be helpful. So I'm going to go to, so if I were to put this and then once again, I kind of just show where it hits. Okay, you could come up with some additional points too. The y-intercept is the one I keep going back to. That's kind of an important one. Where does it cross the y-axis at? We really want to pay attention to that. And then the asymptote is another big one. If you want to get some other points, you could do that. But we got to get some key points to kind of use. Okay, so the good thing is we've done all the transformation stuff before, right? None of that is really kind of new stuff. It's just been a while since we've talked about some of those changes and things. There's a lot of different scenarios or ways that we can use exponential functions. One of those most common ways is one of the coolest things, I think, is with money, okay? And being able to watch your money grow compound interest. If you, most of you guys have taken personal finance by now, and so you've kind of talked about compound interest and being able to watch your money grow. And it's not just sitting in a savings account or a money market account where it's not really growing much. If you're investing it and you're doing things, you can see that money grow exponentially and see the path that it grows. And it should take off. The more you add to it and the more time you give it, the more compound interest you should be able to earn over the years. And so there's a couple of different compound interest formulas. If you're just doing a simple interest formula, that's a little bit different. The first one we're going to talk about is compounded by some kind of time increment. Okay, and so the different types of time that you might see would be monthly, quarterly, semi-annually, maybe annually. It's just how often do I earn interest based on the account that I have. Okay, the formula. Got a lot of variables in this. Okay, P is going to represent the principal. That's how much money I invest. I take $5,000 and put it into an account. And then what does it grow to over time? R is what we call the interest rate, so I'm just going to call it the rate, R for rate. Usually it's given to you as a percent, but we always want to change it to a decimal. So for instance, if I gave you 6%, I would change that to 0.06. We can't just put it in as 6 because then it's going to look like you made a really big chunk of money, but unfortunately they won't pay you out that money. Okay, N is the number of compounds. Monthly would be 12. Quarterly would be 4. 4 times a year, every quarter. It breaks the year up into fourths, basically. Every quarter, they're going to give you interest. Semi-annually would be 2 times a year. Every 6 months, they're going to earn interest. Okay? So some different accounts that you might see, like a savings account. At the end of the month, at the end of March, you might get a statement that says you earned this much money in your savings account this month. So at the end of each month, they'll give you a statement, and savings accounts usually don't earn very good interest. Sometimes you'll get like a quarterly. Like I remember my kids did a savings account when they were younger, and they only earned interest every quarter. So the savings account didn't earn interest every day or every month. It only did it at the end of each quarter, and it wasn't very much money. Okay, it wasn't a money-making account. It was just there to save it up over time, and it earned a little bit of interest, but not very much. And then semi-annually, probably not one of the more common ones, but it could be, and you just do that 2 times a year. Annually would just be 1 time a year, and so that's even probably worse because you only earn interest 1 time a year on an account. Okay, and then finally, T is time, and time is always in years. How many years has that money been in the account? Okay, towards the end of the lesson today, I'm going to kind of help, I'll kind of go through a problem from the homework with you and kind of show you how it's set up, and I'll give you some helpful hints on that. 2 things here. Notice on this formula that the N is used twice. So if I say quarterly, I'm going to put 4 here, and I'm going to put 4 here. So that's the one number that's used twice. The exponent, when you put this into the exponent, then you're going to multiply these 2 together. Sometimes you want to make sure that maybe you put those together or put it in parentheses. Most of your calculators, you should be able to put this all in at once, but you got to be really careful about order of operations because there's lots of things going on within this equation. You got division here, you got parentheses, you got addition within there. You probably want to put this in parentheses to make sure those get multiplied together. So you just want to make sure to do all of that. So if we just do a real basic example here. If I said how much, and I didn't talk about A is, but A is the amount that I have in the account at the end. After 5 years, how much do I end up with? So if I tell you that I invested $5,000 at 6% interest, quarterly for 10 years. We're going to put this into our calculator. Make sure you change that 6% to a decimal. Quarterly means 4. And then my exponent would be 4 times 10. Okay, you can try putting this all in at once. If you would get your calculator out, let's just try putting this in. You can try putting it in all at once. Some people like to do it like one step at a time. If you were going to do it one step at a time, then you always do order of operations. So I would do the division first, add it to 1, raise it to the exponent, and then multiply by 5,000. So if you're going to break it up step by step, those would be the 4 steps I would do it in. Or you could try putting it all into your calculator at once. I don't have 8 for this because I just made these numbers up. Okay. And since we're talking about money here, is that what everybody got? Does that look right? Okay. So not bad, right? You started $5,000, you didn't add any more to it, and 10 years later, I now have $9,000 in there. So that's why I think compound interest is pretty cool, right? In 5 years or 10 years down the road, now 6% is pretty good interest, okay? But on most investments, they say you could maybe get 8 to 10%, so you might even be able to make a little bit more than that. Right now, the stock market is tanking because of the Iran and everything else going on with oil and all that. But so right now is not a great time to invest, but over time, the stock market can be a pretty good friend of yours. And so the earlier you can get started, the better off you could be. Go. I had $5,000, 6%, and 10. Then we end up making just a little bit more money. Okay, so it's a little bit better deal than quarterly or semi-annually or monthly. Okay. You've seen this before, I think, but we have a new number today, and this is what we call the number E. Okay, you might say, I've never seen this before, but I think you have. Because we do this a lot, we use this a lot with what we're going to do later on in the chapter especially, but we're going to see it a little bit today because there's another compound interest formula that uses this that's probably a little bit more common. The number E is an approximation. I kind of think of it as kind of like pi. It goes on forever, okay? And it's called the number E because the guy that came up with this, his last name was Euler, starts with an E, E-U-L-E-R. And so he got to name this number by himself. And so he named it after himself, and he called it the number E. It's used in a lot of banking principles, and it's used in some of the log stuff that we're going to do later on in this chapter to help us find different things. If you look at your calculator, most of you have, I think it's right above maybe the division button on the TIs. You have like a little E. If you hit like second E and hit enter, it'll give you the approximation for E out to maybe 9 or 10 decimal places. If you have E to a power, you could take E to the first power, and that would also give you it's probably going to be a little bit longer decimal than that. Okay. Everybody find E in their calculator? Okay. So you could use this for a lot of different, just basic, I could do e to the third power. So if I take e to the third power, what do I get? If we round it to like the nearest hundredth, let's say, we get about like 20.09. So it's taking this number, but it's taking the whole thing. It's taking, the whole approximation for it and raising it to the third power. And so we're going to get decimals in a lot of those cases. What do you think would happen if we took e to the 0 power? Just 1. Any number raised to the 0 power is always 1, even if it's e, right? E is still a number. And it's kind of weird because you might say it's a letter, but e represents a number. The most common place that we're going to see e is we're going to do what we call compound continuously. So it's a different kind of compound. The key word here is continuously. This is probably the more common way of money being compounded, because if you had a retirement account and you looked at your retirement account, you see that money changing all day long. Okay, as the stock market is open, your account is changing. It's going up, it's going down. It's compounded continuously, and that's how most retirement accounts work, is they're compounded continuously. The formula for this, I call it the PERT formula, because that's kind of the way it's spelled out, but it has the number E in it, okay, and it works the same way as our last one. P is still the principal, E is now the E, right, number E, R is still your rate, T is still your time. So if I go back to the same example that I had just a second, I'm going to use the same numbers. And just show you that you get a little bit different answer here. Because it's compounded a little bit differently. So if we go 5,000, and then you're going to use e to the power. And I would say make sure that you put the 0.06 times 10 in parentheses. This calculator's not doing it. What are you guys getting? Okay. And how much cents? 59. Okay. So it's still over 10 times, it's still 6%, but because your money is continuously compounded, because you're continually making money each day, each moment. Okay, so those are the two different kinds of compound interest formulas that we're going to see. All right. I'm going to go ahead and put the assignment up here for you. There's probably a few other things that I want to get to, but there's a lot of stuff in this section. But I want to make sure I get this up here for you before we run out of time. There's a lot of them that are going to ask you to do graphing. You can use your calculator to graph those. Try to just get some key points. Watch for the asymptotes. On any of the ones that have shifting or movement taking place, make sure that you identify like what kind of movement is taking place. On number 53, that's the one I was going to spend a little bit of time talking about, and we can maybe do that at the beginning of the hour tomorrow. It asks you to write an equation. It's a compound interest equation. It asks you to graph it, okay? And then it asks you, part C, it says, what is t equals 0, t equals 2, t equals 5, and t equals 10. You can plug that in 4 different times, but what I think probably would be easiest is to put the equation into your y equals, okay? And then just go to your table and see what's my answer for 0, 2, 5, and 10. We'll maybe talk about that a little bit tomorrow.